Hi everyone, welcome back to 30.100 Computational and Data-Driven Engineering. This week we're going to move on from statistics. We've been looking mainly at errors and how they build up. We've also looked at distributions and how we can break down a distribution into different groups and see if they're statistically different. And last week we looked at design of experiments and we used analysis of variance to understand which configurations of an experiment are statistically better than the others. This week we're going to move on to root finding algorithms, so slightly different, no longer statistics. In particular, we're going to look at 4 different algorithms: fourth position, bisectioning, Newton-Raphson, and fixed point. And finally, I'll very briefly discuss how these can be combined. So after this class, you'll be able to understand the difference between open and closed root finding methods. You'll be able to graphically interpret and describe these different methods. You should understand something about the way that these different methods converge. And you'll also understand and be able to describe the types of problems that occur with these different root finding methods. Finally, you should be able to propose a way to find roots using some of these algorithms that we're discussing today. So the reading for this week is the Chapra's book, chapter 5. That will describe closed methods for finding roots, and then open methods for finding roots, and that's chapter 6.1, 6.2, 6.4 of Chapra's book. In this week's material, there'll be 1 lecture video. This is it. There'll be 4 case problems, and we'll continue with the 1D project as well. So let's start out with an example. Let's imagine that a granny is parachuting and she can record her velocity as a function of time, and she could make a table of this data. So that any particular time would be, we know the granny's mass, we know the gravitational acceleration due to gravity, we know the velocity, and we know the time. So we've got all of the information apart from c, which is the granny's drag, how much she's resisting the falling due to the air blowing her back up. So how can we find c in this example? It's actually very difficult. It's very difficult to do this analytically. In fact, impossible, I believe. So we cannot easily rearrange this equation for c. We cannot restate it explicitly for c. So we need to find some other way of finding the value of c that satisfies these particular parameters of mass, time, gravity, and velocity. If we subtract the velocity from both sides, we know that this part of the equation should equal 0 when c is the correct drag value. So what we could then do, because we know the mass, the granny is able to know her weight, we know the acceleration due to gravity, and we know the time and velocity at every point. So we could just try different values of c until this part of the equation is equal to 0. In other words, we can find the root of the equation. So we could just do this randomly, trying many different values, but it wouldn't be particularly efficient. There must be better ways to find the roots of equations. So rather than randomly trying different values of c, there are some slightly more sophisticated methods, which is what the topic of this class is. So as an example, let's just start with a quadratic equation. How might you find the roots of this quadratic equation? So probably the first method that we'll try is applying the quadratic formula. So for a quadratic equation of the form y equals ax squared plus bx plus c, we can take out the factors a, b, c, put them into this quadratic formula, and the values, the the result will be the values of x which are at the roots of the roots for this equation. So this is straightforward, but what about when we have a more complicated equation? Perhaps it's a higher order polynomial, or maybe it's a function like a transcendental function like a sine curve or an exponential function. How would you find the roots of an equation like this? So we could try an analytical approach, but sometimes there are no analytical solutions. We could try plotting and graphing the function, but this lacks precision, and also when we have more complicated equations or multidimensional equations, it becomes very difficult when we have more than 2 dimensions. Another approach might be trial and error, but this is very inefficient. So we need some other method, a computational method. There are 2 general classes of root finding methods that we're going to discuss today. One of them is the bracketing method, and the other one is an open method. So the bracketing method basically consists of giving 2 values where you think the root might lay between, and the open method, usually you just give one value and you iterate and get down the curve following a gradient, usually if you're using Newton-Raphson, until you hit the root to within some precision. We're mainly going for the bracketing method. We're mainly going to look at the bisection and the false position method, and for the open method we're mainly going to concentrate on fixed point and Newton-Raphson, and we'll briefly discuss the Brent method. So the first method that we're going to look at is the bracketing method. So the first thing I would do if I was using a bracketing method is plot the function. And I can roughly see from this function that we have a root at around x equals -2 and a root at x equals 0.5. So I might set up the bounds for the bracketing method, or the area that the x range that I'm looking for the root to be around those points. So for this root that goes between -3 and -2, between -3 and -2, I would effectively set up a bracket to bracket and only look at that particular part of the function. Equally, I'd look between 0 and 1 for the second root. So the bracketing method exploits the fact that as the graph changes through the root, it goes from a positive value to a negative value. So there's a change in the value of the function either side of the root. So the bracketing method exploits this fact. So first of all, we have to set up some lower and upper bounds. So I've called xl the lower bound and xu the upper bound. And we basically use, if the function changes sign when it goes from the lower bound to the upper bound, the product of f of xl times f of xu should be less than 0. It should be negative if these signs are opposite, if these functions are opposite to either side of the root. So if f of xl times f of xu is less than 0, in other words, if this point multiplied by this point results in something that is negative, then we know that there exists at least one root between those upper and lower values of x. And we also know that there's an odd number of roots. The problem is that if the function is tangential to the x-axis, so if the root comes down and then it skims the x-axis but doesn't really pass through it, there can still be a root there if it touches the x-axis, and we will not really find it because the function will not result in something that is less than 0 when we make this product of f of xl and f of xu, because both sides of the function would be positive in that case, And it also doesn't work if there's a discontinuity in the function. So it's always good to use these bracketing methods in conjunction with some sort of graphical analysis like we're doing here. So once we identify the places that we want to test, we might, to see if there's a root, we might set a lower bound here of -5 and an upper bound of -1, and clearly we're looking for this value close to x equals -2, and we can test the function at -5. So then we find the halfway point. So we look at the halfway point, which in this case is x equals -3, and I check the x equals -5 and x equals -3, and I see that both of those values are positive for the f of x at -5 and f of x equals -3. When we do this product, we will get a positive number. So there's no root in this range. However, if the lower bound becomes -3 and the upper bound becomes -1, clearly this function changes from a positive value to a negative value. So when we do this product, we'll see a negative result. So we know there's a result. We know there's a root somewhere between x equals -3 and x equals -1. So that's this point. So then we select these two new bounds as the upper and lower points where we're going to search and search again. So the next iteration, we would halve the range again and look at these 2 points. Now I'm going between -3 and -2. So when x is -3, f of x is positive, and when x equals -2, f of x is negative. So when we multiply those two f of x's together, we will get a negative value. So we will conclude that there's a root somewhere between -3 and -2. And then we can do the same again and iterate over and over again. So between -3 and -2.5, if I look at the f of x, both of those values will be positive. So there isn't a root in that range. But if I look between -2.5 and -2, we will now see that the function has changed sign. There's a positive value of f of x at f of x -2.5, and a negative at f of x equals -2. So we know there must be a root somewhere between -2 and -2.5. So this is the process, and we can keep doing this until we reach a desired accuracy. And this is called the bracketing method. And then we eventually settle upon the root being within some bounds. So this slide is another example. It's exactly the same process which I just described on the previous page, only we're putting real numbers into this function. So in this case, we know there's a root between between 12 and 16 from graphing the function, plotting the function. So we guess that the upper and lower bounds of the brackets should be between 12 and 16. Then we calculate the halfway point. That's our next guess. So the halfway point will be 14 at this point. And then I can test whether f of 12 and f of 14 leads to a negative number. It doesn't. So I conclude that there must not be a root between 12 and 14. So then I check between 14 and 16, so these 2 points. This time the function turns negative. This product of f of 14 and f of 16 becomes negative, so I know there must be a root somewhere in that range. And then we can repeat the process over and over. Each time I will be narrowing down, honing in on where the root is. So we can keep honing in on these roots, keep halving and bisecting until we get to a particular tolerance. That tolerance can then be the condition to stop this honing in and declare that we know the root. But before doing that, we need to understand what the stopping criterion should be. One idea might be to set a particular error, a particular tolerance as a stopping criterion. So here is one method to calculate the error. We can look at the new root and compare it with the old root. So we calculate this change in going from the previous iteration to the new iteration, and then compare that to the actual value of the new iteration, and this will give us a percentage error in the estimate of this new root. We can then say, okay, we want our estimate of the root to be accurate to within 1% of its value, and then if this percentage error becomes smaller than 1%, then we can tell the bisectioning method algorithm to stop bisecting and to output the root to within some specified tolerance. So one of the big advantages of the bisectioning method is that we can calculate the number of iterations that we need to do to reach a desired accuracy. So this is a derivation of that equation that will allow us to predict the number of iterations. If our initial range between upper and lower values is delta x, after one iteration, the new range will be delta x of the previous iteration divided by 2. So we'll have doubled our accuracy. After a second iteration, we will have quadrupled our accuracy, because the second iteration will be half of delta x divided by 2. And after 3 iterations, the accuracy will be an eighth of the original accuracy. So you can see that the accuracy scales inversely proportional to 2 to the power of n, where n is the number of iterations. So if we have one iteration, we will have halved the tolerance and doubled the accuracy. If we have 2 iterations, we will have a quartered the tolerance and quadrupled the accuracy. And 3 iterations, we will have an eighth of the tolerance. If we rearrange this equation for n, we can very easily calculate the number of iterations it would need to reach a particular tolerance. So this is what this equation is at the bottom. Okay, so we're going to move on to a new method now, which is the false position method. It's also a bracketing method, like the bisection method, but it's a lot faster than the bisection method, so this is a good reason to use it. It works by enclosing, just as before, enclosing the root with two values, a lower value of x and an upper value of x, calculating the value of the function at these 2 points, at these 2 values of x, connecting those 2 points with a straight line, and where the straight line intersects the x-axis, this will be our new root, our new estimate of the root. So the trick here is that we need to define this straight line that goes between these 2 points. Now these 2 points have the same gradient. Because it's a straight line, the gradient has to be the same. So we can write down the gradient between xl and xr. So that's this part of the equation, being equal to the gradient between xu and xr, which is this value of the equation. So clearly a gradient is the difference in the x-axis divided by the difference in the y-axis. So the difference in the y-axis divided by the difference in the x-axis. So that's what this part of the equation represents. And the gradient going from xr to xu is the difference in the y-axis, so f of xu, divided by the difference between xr and xu. And then if we rearrange this equation for xr, we can get it in this form. And this form is useful for predicting the new value of the root based on the upper and lower bounds and the values of the function at those upper and lower bounds. To do this derivation, please have a go yourselves. If you get stuck, it's also in Chapra's book. So we can go through iterating through applying this technique over and over again, where each time we update either the lower bound or upper bound with the new guess of the root. So XR replaces the initial guess that yields the same function value as XR. So if XR is positive, f of XR is positive, then we should replace either f of XU if that's positive, or f of XL if that's positive. We choose which one depending on what f of XR is equal to. So the false position method tends to be a lot faster than the bisectioning method, but that speed comes at a cost. The cost is that the function tends to get stuck, or one of the bounds stays fixed. It doesn't change as the function iterates. If this happens, it's a good idea to include a counter in your code that checks if the bounds are updating in each iteration. If they're not updating, you can modify the code slightly to like halve the bounds, or divide the bounds in half, and look at each section a bit like the bracketing method. This is called the modified false position method. So we've learned a couple of methods that we can use, closed methods that we can use for finding roots. What if your function has many roots, like this particular function? One method that you might try is having a bracket which you traverse across the x-axis, looking for changes in the sign of the function values at the lower and upper bounds. If there's a change in the function value, like from positive to negative here, we know that there's a root in between. So we could initially run through the whole of the x-axis, or within some range that you consider acceptable, trying to identify sign changes, and then marking those sign changes down for further examination. Clearly, in this particular area here, there are lots of roots in a very small, close to one another, very close proximity. This would do, to identify all of these roots correctly, you would need a very small bracket, and this would be very slow to run a small bracket over the entire range of the x-axis. Therefore, it's probably a good idea to first of all identify where potential roots are, then examine them in a little bit more detail. It's also useful to check whether the function's first derivative changes sign at the bounds. If it changes sign, then there's likely a turning point, as in this case. So we see that the first derivative, if we put a lower bound here, the first derivative is negative, and at the upper bound, the first derivative is positive. So in this case, there's a change in the sign of the first derivative, and there's a turning point in between. So we can also use those sorts of facts to understand where roots are and where turning points are and how the function behaves. So until now we've focused on closed methods. So those are methods that require an upper and lower bound, and the root needs to be in between. We can also actually find roots by just defining one point, and these are called open methods because we're not enclosing the root. So that is shown on this slide. You can see here that the bracketing, we give 2 values and the root is halfway in between, but in an open method we give just 1 value. We calculate the gradient. A typical method might be calculating the gradient, projecting onto the x-axis, moving up, calculating what the f of x value is there, calculating the gradient, and then projecting down to find where the root is. However, these methods, open methods, are more likely to have convergent problems. For example, with this particular function, we start at this value here, we go across on the tangent, we find the next value where we should go up, and then find the x value. But now, because of this turning point, we are going to go away from where the root is. So there's going to be a convergent problem. It's not going to find this particular root. So we'll see when we use Brent's method that maybe a good technique is to combine bracketing and open methods. So the first open method that I want to discuss is the simple fixed point method. So this works by taking a function that has roots. This has roots because it's equal to 0 here, and then rearranging it so that x becomes a function of itself. So x equals g of x here. So let me give you an example. Let's say we have the function e to the minus x, and we want to find the roots, so at the roots this will be equal to 0. We can rearrange this to the form x is a function of itself. X equals e to the minus x now, just by rearranging this equation at the root. And we can now write this down in an iterative form. We can say that the current value of, we take the current value of x and we calculate its exponential, and that will predict what the next version of x should be, that we can then replace back into here and recalculate the new value of x. And we can iteratively go round in this cycle, and eventually we will get a converge on the root. So let's continue with this example. So this is an example taken from Chopra's book. So we're trying to find the roots of f of x e to the minus x minus x. And we'll start with an initial guess of x equals 0. So we rearrange this equation into the form shown on the previous page. And our initial guess is plugged into here. So x equals 0. And our initial error is enormous because we don't have any previous guesses. But this gives us the next value of x. So if we put 0 in here, e to the minus 0 is 1. So that gives our next value. And again, we have a large error because the value of our guess has gone from 0 to 1, so 100% error. Then we put the new value of x into here. So 1 is the new value. So now we have e to the minus 1. And the output is 0.367. And that becomes our new value of x, which we put back into here. And then the output becomes 0.69, and we plug that back in there. And we keep going through and going through and going through. And very quickly, well, relatively quickly, we converge on the correct root with a very small error after 10 iterations. So this is the mechanics of how this process works. You can imagine coding this with some sort of while loops to reach some specific tolerance in the absolute value. So when we have two functions that equal to one another, this represents a crossing point in the y equals x graph. And this is exactly where the root would be, right? It'll be at this point here. So in this fixed point method, we initially start at some value of x, and we calculate the value of g of x at that point. In the previous case, it was g of x was equal to e to the minus x. And that gives us the new value of x, which we put into the new function. So the new value of x is read off from this point, and that goes back into g of x to calculate the g of x curve. And that gives us the new value of x that we should put in. And slowly, we converge on the root where these 2 points cross. So this is repeated over and over until we reach some particular accuracy. So the second open method that I want to discuss is the Newton-Raphson method. So this is a much faster method than the fixed point method. And so it's also faster than the closed methods as well. It converges very quickly. So the way it works is you have a guess of what you think the root is. You calculate the value of the function at that root, which is this part. And then we have the gradient. We calculate the gradient at that particular x value, at that guess value. And then we use that information to project downwards to find the new value of the guess. And then we do the same thing. We put this back into the equation, this new x value back into the equation, and we find the gradient, we evaluate the gradient, and we use that to project downwards along the gradient until we hit the x-axis again. And then in just a few iterations, we'll be very close to the root of the equation. So as I said, it uses a first-order Taylor expansion. And if we rearrange this Taylor expansion for the xi plus 1, we can have this iterative approach to evaluating the guesses and refining the guesses. So we start with the Taylor expansion. We've rearranged it here for the to show what the gradient would be, and of course we're evaluating this function at 0. So f of x I plus 1 is 0 just here. So that's why this is 0, because we want to find a root, and the root is at 0. So we put this into here, and then rearrange again, and then we can rearrange for xi plus 1, which is the next value of x. So if we have a guess, we can calculate the next value of the guess, or the next iteration, by having the initial guess and dividing the function value by the gradient. And this will give us the new value. So this is a highly recommended approach for finding roots. So the Newton-Raphson method does fail sometimes, and these are some of the common reasons why it might fail. So first of all, if you have some kind of inflection point, so if we start off at x equals 0, this is our initial guess, and we're trying to find this root here. We project upwards and then project across along the gradient to get our new value. But you can see that we haven't really improved the guess. The difference between the new value and the initial value and the root is more or less the same. So we go through again, we go down, but now we're even further away. And then we do the same thing again, and we go even further away. So the shape of this kind of ogive shape is very difficult to find the roots of using the Newton-Raphson method. Another problem is local minima or local maxima. You can see here our initial guess is just here. We project downwards to find x1, go up, project downwards to find x2, go up. But each time we're getting further and further away. So the Newton-Raphson method doesn't like local minima. So complex roots are difficult. Multiple high-frequency roots can cause problems. So if you have lots of roots close to one another, we have a problem where we might jump around between all of these roots. So we need to find some other method to evaluate very close together roots. And very similar to this local minima problem, if we have a situation where the gradient goes to 0, we get a divide by 0 error. In other words, we're going to an infinitely far away in x. So we have to watch out for those, and also try to find ways of overcoming these issues. So if you're building your own root finding algorithm, I highly recommend that you initially plot the function to try and find out roughly where the roots might be. Once you have a solution, once you've found a root, substitute it back into the original equation and do a sanity check. Clearly, if the root is really a root, and if you found it properly, when you substitute it back into the original equation and evaluate the equation at that root, at that converged root, the equation should equal 0. So do that sanity check. It's also a good idea to include a maximum number of iterations, so your code doesn't enter any infinite loops if there are convergence problems. And this divide by 0 problem for the Newton-Raphson method, there should probably be some sort of check in your code to check for these sorts of issues. So far we've looked at open methods and we've looked at closed methods. Open methods tend to be less reliable but very fast. Closed methods tend to be very reliable but not very fast. So maybe there's a way we can get the best of both worlds, and there is, and that's called Brent's method. So Brent's method first of all tries an efficient open approach, an open method approach, such as the Newton-Raphson method. But then if it fails, the method will automatically switch to the bisection method. And this process can be repeated, switching between the two different methods until we reach convergence. So this is the Brent method, and I think there's a Brent method function built within Python that we can employ. So if we just have a look at this chart here, it compares the relative speeds of these different methods. So bisectioning tends to be 10 times slower than Newton-Raphson method. Newton-Raphson is the fastest method that we've looked at today. But as I said, Newton-Raphson has a few disadvantages. It can easily get stuck. Also, we need to evaluate a derivative as well. So we either have to put the analytical derivative into the function, or we have to computationally compute the derivative. So it could add extra computational requirements. Bisectioning is slow, but you can predict the number of iterations you need to get to a specific tolerance, and it's guaranteed to converge if there's a root really in the range. False position method is probably not the best choice. Usually bisectioning or Newton-Raphson or some combination of the two would be used, or secant method, which we haven't looked at in today's class. So that pretty much summarizes it for this week. We've looked at the principles behind 4 root finding methods: bisectioning and false position, which are both closed methods, and then the fixed point and Newton-Raphson methods, which are both open methods. There are many problems for open methods that stop the system from converging, but it tends to be very fast. Closed methods are slower but tend to be more robust. The best of both worlds comes from Brent's method, which combines the speed of open methods with the robustness of the bisectioning closed method. So in the coming week, we'll have a go at programming some of these methods in Python. Okay, thank you and see you next week.